Good morning, everyone. Today we are going to continue our talk about applications and processing of ceramics. This is the part 2 for this topic. And here is today's objective. We want to learn the processing of ceramics. First, we talk about classification of these ceramics. We talked about this one in our previous class, but now I want to refresh your memory about this classification of ceramics. The ceramic materials, and this is a very broad. Uh, this is a very broad name. Broad. This is a category of material. Usually we divide these ceramic categorize these ceramic materials into 6 subcategories. First one is glasses and clay, refractories, abrasives, cements, and advanced ceramics. Advanced ceramics, I want to mention this one a little bit more because people have used these materials for engine, rotors, valves, bearings, and sensors. Also, abrasives are very important also. And for example, sandpaper, cutting, and polishing. And as I said, and I have introduced this slide to you in our previous class, and I hope you have already understand all these things um, and internalize these concepts, these categories um, in your memory, and in your knowledge database. So we'll continue our talk. So here is the ceramic fabrication techniques. And we talk about how we fabricate the ceramic material. And we have glass forming processes, and we have particulate these forming processes and cementation. These are 3 big categories. And within this big category, we have um, pressing, blowing, drawing, and fiber forming. So for glass forming processes, and for particulate forming processes, we have powder pressing, and we have hydroplastic forming and slip casting, tape casting. For this powder pressing, we can have hot, uniaxial, and isostatic. These are small groups. And then this is drying, and then this is firing. And so this is the steps. Any questions regarding this slide? No questions? We move on to next slide. Next slide, we talk about this glass forming and we know that the glass utensils have been used in our daily life almost every day. This blow of glass bottles, for example, here. So we have Parisian mold here. This is a mold here, and so we have this is the gob here. This is a gob in this mode, and then we pressing operation, and we use this is the this rod, special rod to press, and this is a gob of the glass. So this is one thing. Another is a suspended the person. This is a suspended person here. So here is uh, a finishing mode, and here is a compressed air. You can use compressed air and to blow. This is the red, this glass, and then this glass and will go will near this is the internal wall of this is a container of this mode. This is pressing. And pressing, we can use the plates, cheap glasses, and glass formed by application of pressure. So mold is steel with graphite the lining. So this is fiber drawing. Here is this is glass. This is a molten glass can go here, go down, okay? Going down, and this is weld up. This is called a fiber drawing. So this the ceramic is, we call this a fiber drawing. And sheet forming here, and continuous casting here. So this is raw material. Okay, this is raw material. This is molten glass here. This is a melting furnace, and then going down. So here is the rollers, and rollers going here, and then this is liquid tin, and liquid tin is here. The melting material will be floating on the liquid tin. So here is a heater, is a combustion, the gases, and this go to the heater. So this controlled atmosphere given use some prescribed the atmosphere, and then it just have another roller. So this is annealing, right, furnace. This is annealing, and then after this solidifies, and we just cut piece by piece, and this we have this cutting section. So this is a float blast furnace. So this is a very useful and famous one in this glass, the forming industry. And the glass, the structure, basic unit, and we use, without loss of generality, we use this silicon and oxide, this tetrahedron. So here is a silicon, 1 silicon and cation, and 4 the oxygen ions. Cones is crystalline silicon dioxide. So you can crystalline, it is these atoms, they are arranged in some pattern. So glass is non-crystalline here. This glass is non-crystalline. Amorphous means that this is atoms, and they are not ions. They are not arranged in some pattern. For example, fused silica is silicon dioxide to which no impurities have been added. Other common glasses contain impurity ions such as sodium, calcium, aluminum, and boron. This is boron have 3 positive charges. So here is a soda glass. So you can see potassium, silicon 4 plus, and this oxygen, and 2 minus these ions. And glass properties, and we know glass very well because, as I said, and glass utensils are widely used in our daily life. So glass properties, a specific volume, and we have a specific volume 1 over rho, and versus temperature. And the specific, whenever you see the specific, it is a specific volume. Okay, so 1 over rho, and so this is something per unit, the mass. So this is a specific volume, and so here is crystalline material. So this is a crystalline specific volume. You can see, and so here Tg, this is a glass. So here is a glass temperature, and so here is a melting temperature, glass recrystallization temperature, and so here is a glass transition temperature. I'm sorry, this is glass here, and glass do not crystallize and change in slope in the specific volume and curve at the glass transition temperature Tg. Transparent and no grain boundaries to scatter light. So this is very good, and no grain boundaries to scatter light. So crystalline materials the crystallize at melting temperature and Tm, and have abrupt change in the specific volume at Tm. You can see crystalline disordered. So here is a glass. Okay, so this is any questions regarding this slide? No question. We move on to the viscosity. And viscosity, and how do we define viscosity? Viscosity means it relates shear stress and the velocity gradient. And so this is a gradient. Okay, whenever you see gradient, it means that the change of something with respect to the position or location. And so the dv, velocity, the change of velocity with respect to position in y. So this is shear stress here. And so this one is used to define the velocity. It equals tau divided by the velocity gradient. And this eta has units of pi and pi. This is the second Pascal. I'm sorry, Pascal. So log glass viscosity versus this temperature. Viscosity decreases with temperature, right? We know that. And if we elevate the temperature, viscosity decreases. And we know that means the sticky material becomes almost stickless. So this is the viscosity decreases. And you can see this temperature. This is a figure. This is a temperature and degree C. So this is a temperature, viscosity, Pascal, and a second. And we can see for all these glasses, all this is the glasses, the viscosity decreases substantially if you elevate the temperature. And so here is a melting point here. Right, so this is the temperature. So here is a softening point, and here is a working range. This is the working point here. And so this is the porous liquid, the glass for this one. So here is a soda lime glass. And so here is a 96% silica glass. So here is a fused silica. And starting point, stream point, and annealing point. And so this is a figure gives detailed information. So what is a fused silica? If this is the material contains more than 99.5% of silicon oxide, and Vicor is 96% silicon oxide and 4% of this boron oxide. This borosilicate, and so this is the 30% of B2O3, 3.5% of sodium oxide, along with 2.5% aluminum oxide. And soda lime glass, 70% silicon oxide, the balance sodium oxide and this calcium oxide lime. So this is a different the glass types, and so you might know this one very well. You need to know this one clearly. Okay. And then we talk about the log glass viscosity versus temperature. There are several important observations here. The melting point corresponds to the temperature at which the viscosity is 10 Pascal. Second, the glass is fluid enough to be considered liquid. So this is a melting temperature. The working point represents the temperature at which the viscosity is 10 power 3 Pascal second. The glass is easily deformed at this viscosity. The softening point, the temperature at which the viscosity is 4 times 10 power 6 Pascal Pascal second, is the maximum temperature at which glass piece may be handled without causing a significant dimensional alteration. The annealing point is the temperature at which the viscosity is 10 power 12. At this temperature, atomic diffusion is sufficiently rapid that any residual stresses may be removed within about 15 minutes. This annealing the point. The stream point that corresponds to the temperature at which the viscosity becomes 3 multiplied by 10 power 13 Pascal second. For temperatures below the stream point, the fracture will occur before the onset of plastic deformation. The glass transition temperature will be above the stream point. So these observations are very, very important. I want you guys to know these, to internalize these observations in your mind, and change this knowledge into your own knowledge in your knowledge database. And then we talk about heat treating glass, and we have talked about heat treating for these metals and metal alloys. Now we talk about heat treating. The same thing, the same principle. Annealing removes internal stress caused by uneven cooling, and tempering and puts surface of glass part into compression tempering, and suppress growth of cracks from surface scratches and sequence. You can see before cooling, hot, initial cooling, cooler on these two sides, and hot in the middle at room temperature. Okay, at room temperature, and so here's a compression on these two outer layers, and inside and this tension. As a result, surface crack growth is suppressed. And I also told you guys when we talk about this case hardening, and the case hardening means that we put some samples, specimens in the chamber, sealed chamber, with this is a small carbon items, for example, the liquid or this the gas, methane, and we use methane CH4, and so after some time, and the samples that we put in the chamber will be hardened on the surface, and also in the same time on the surface we will have this beneficial compressive residual stress on the surface to enhance the fatigue life of this specimen. And then we talk about particulate the forming and hydroplastic forming and hydroplastic. Okay, and so it's a mill, grind and screen on constituents, and desired particle size, extrude this mass into a brick. So this is a force, this is a ram, this is a billet, and so here is this die holder and your container. At the very beginning, this initial cross-sectional area A, this is the desired cross-sectional area, this extrusion. And then dry and fire the formed piece. You need to dry and fire it. Slip casting. So slip casting means mill, this grind, okay, grind, and screen constituents, and desired particle size, mix with water and other constituents to form the slip. This is a slip. A slip casting operation. So here, pour slip into the mold, absorb water into the mold. You can see this is shrink, and this slip shrinks. And the grain ceramic, this is a grain ceramic. Then pour this one, pour slip into the mold, and drain mold, and this grain ceramic. And then dry and fire the cast piece, and dry and fire the cast piece, the grain ceramic. Typical porcelain composition, porcelain, right? Porcelain also are widely used in our daily life, and 50% is clay, 25% is a filler, and for example, corns, finely ground filler, and another 25% is a fluxing agent and feldspar. So these alumina silicates plus potassium, sodium, and calcium upon firing and form low melting temperature the glass. This is porcelain. This is porcelain. Then we talk about hydroplasticity of clay. And clay is inexpensive, right? So clay, have you guys ever played with clay? And when I was young, I played clay. I used the water and to play the clay to form different kind of shapes. And when water is added to clay, water molecule fit in between the layered sheets, right? Layered sheets reduces degrees of van der Waals bonding. Van der Waals bonding is among these layers and is between the layers, which is kind of weak. When external forces applied, clay particles free to move past one another and become hydroplastic. So this is the structure of kaolinite, the clay. Here, this is kaolinite clay. So this is a weak van der Waals. This is for bonding. So this is charge neutral. Right? This is charge neutral. So this is charge neutral also. This is shear. And any questions regarding this slide? And then we talk about drying and firing, and I have mentioned these two terms several times in our previous slides. So what is drying? As water is removed, interparticle spacings decrease, called shrinkage. This is drying. This is drying here. So you can see this is white body. You can see we have the water inside. This is the particles, and between the particles. And this is a partial dry. When you dry, there's a lot of water disappears. And here it is a completely dry. So drying too fast causes sample to warp or crack due to non-uniform shrinkage. And so this then talk about firing. Firing, as the name suggests, we use a fire to heat treat this material. And heat treatment between 900 degrees to 1400 degrees C. Vitrification. Okay? So what is a vitrification? Liquid glass forms from clay and flux, flows between silicon dioxide particles. Flux lowers melting temperature. Because the flux, it is easy to be melted. So the whole thing will, for the whole sample, if we end this flux, the whole sample's melting temperature will be lowered. So folks, look at this is the micrograph. So these are silicon dioxide cones, small particles, and so here is a glass formed around the particle. This is the graph. And then we talk about the powder pressing used for both clay and non-clay compositions. The powder plus binder, okay, must have binder, and compacted by pressure in a mold. Uniaxial compression, compacted in single direction, isostatic compression, and pressure applied by fluid powder in rubber envelope, hot pressing, and pressure plus heating. And then called sintering. And sintering occurs during firing of a piece that has been powder pressed. Okay, powder particles, coalesce, and the reduction of the pore size here. You can see it here. And this is a pore. This is a neck. These are green boundaries here. You can see here, and so this pore size is decreased. Aluminum oxide powder sintered at 1700 degrees C for 6 minutes, and you can see this one. So table casting, the table casting here. So thin sheets of green ceramic cast as flexible tape are used for integrated circuits and capacitors. And slip, the suspended ceramic particles plus organic liquid. For example, contains batters and plasticizers. So this is slip. Slip source. These daughter blades here are very sharp. This is reel of carrier film. This take up the reel. This is source. This is support structure. Hardening of a paste. A paste formed by mixing a cement material with water. We know that when we use the cement to do something for our home, and we use the water, and then the cement can become a very, very hard material. Formation of rigid structures having varied and complex shapes. A hardening process, hydration, complex chemical reaction involving water and cement particles. This is a chemical reaction. It should be emphasized that the process by which cement hardens is not one of drying, but rather a hydration in which water actually participates in a chemical bonding reaction. So this is very, very important. I want you guys to know the principle of cement ended with water, and the Portland cement production of mixed clay and lime-bearing minerals. Calcine, when we heat it to 14 degrees C, 100 degrees C, grind into fine powder. And summary, categories of ceramics. We have glasses, clay products, refractories, cements, and advanced ceramics. And ceramic fabrication techniques, we talked about glass forming, for example, pressing, blowing, and fiber drawing, particulate forming, hydroplastic forming, slip casting, powder pressing, tape casting, and cementation. And cementation means the process of adding water in the cement, and then the cement will experience hydration and also a chemical reaction. And heat treating procedures on glass, we have annealing, talk about annealing and tempering, and also particulate formed pieces, we talk about drying and furring. And furring, we talk about the sintering. Any questions so far? And I hope sometimes this semester I will give you a uh, virtual tool and to the professor, another professor's lab, and who is working at another university, and I want you guys to see and how they fabricate the ceramics and how they heat treat the ceramics, especially how they sintering, how they do the sintering of the ceramics. I hope you have a lovely day.